Tens of thousands of airplanes fly around the world every day, and there's a lot that feels surprisingly normal about airplanes considering how ridiculous it is that we have tubes of metal that shuttle many tons of humans and luggage through the air all the time. But if you stop to think about it, a lot of incredible things have to happen to get these awkward machines in the air. And since planes can show us so many amazing things about engineering, physics, and the future of transportation, we decided to make a compilation out of some of our favorite plane episodes of SciShow. Even though the concepts behind airplanes haven't changed much since the days when the Wright brothers were testing planes on the beach in Kitty Hawk, planes themselves look pretty different. One thing you see on most modern-day airplanes are these little things sticking up from the ends of the wings, called winglets. They're there to make planes more efficient, which is a big deal when you're burning through a liter of jet fuel in under 2 seconds. So here's more on how those little flippy parts at the end of the wings can help.
What do you hate most about flying? Is it being cramped in that skinny little seat, not being able to get up and pee whenever you want? Maybe it's the fact that there's always a guy somewhere on your flight who thought that this was the perfect time and place to eat a really giant smelly meatball sub. Well, if you're an airline, the thing you probably like least about flying is drag. Drag is the total of all the forces that a fluid exerts on an object that's moving through it. And air, which is a fluid, can exert all kinds of drag on an airplane. So airlines burn a whole lot of fuel and money fighting drag each time an airplane flies. Now you might think of drag as being just the friction that's caused by the air as it rushes over the surface of the plane or as the plane smashes into it, and that's definitely part of it, but it's only a part. But there's also all kinds of wacky fluid dynamics going on all around the aircraft, especially vortices, swirling eddies of air that form over the wingtips and all along the trailing edge of the airplane's wings. They're a serious source of drag because as each powerful vortex whips around, it basically pushes down on the top of the plane wing while also pulling back on it, effectively sucking the plane backward, which sucks. Because the airline is trying to move 162 people from Minneapolis to Orlando as quickly and safely as possible, and it's hard to do that when the laws of physics are drawing you backward a little bit every time you move the plane forward. That's why engineers invented winglets. Those are the tiny little bits of wing that turn upward at the end of an airplane's wings. They're basically an elegant solution to a complex problem. For a long time, engineers have known that the quickest, easiest way to reduce drag is just to increase the wingspan. The longer a wing is, the less it feels the effects of a vortex. But you can only make wings so long before you have to add extra supports to strengthen them, which in turn adds a lot of weight. But you can achieve a similar effect by just curling the tips of the wings up. That shape interferes with the airflow of the vortices, reducing drag without adding too much extra weight. The idea was actually proposed back in the 1970s when the US was in the clutches of an oil shortage. A NASA engineer proposed winglets as a way to reduce drag by as much as 20%, thereby saving a ton of fuel. It took more than a decade of testing, but by 1989 the first commercial airliner with winglets was introduced. And ever since then, the concept has been tweaked and improved with each new airplane design. Over the years, this has saved billions of dollars of fuel. Today, winglets are commonplace, so the next time you're on an airplane enjoying a tiny foil bag of mini pretzels, and you look out the window to see those winglets, you can take heart in knowing that the airline is using 2.5% to 4.5% less fuel than it normally would. So go ahead and ask for another bag of pretzels. They can afford it.
Engineers and airlines will do a lot to save a little energy, and that's one of the reasons why planes fly so high up, where there's less air to slow things down. But there's a surprising side effect of being up that high. You're exposed to a lot more radiation, since there's less atmosphere in the way to protect you. Even so, here's Michael to explain why you shouldn't really worry.
Every time you fly in an airplane, you're exposed to radiation from cosmic rays, which are high-energy particles from outer space. Pilots and flight attendants are even classified by the Center for Disease Control as radiation workers. But does that radiation make flying dangerous? Well, no. Even if you're a frequent flyer, you probably don't have anything to worry about. See, we're all exposed to very small amounts of ionizing radiation every day, the kind that has enough energy to knock out electrons from atoms, so it can also break chemical bonds or damage DNA. But your body's built to handle things going wrong in your cells by fixing them or replacing any damaged cells with new ones. All this background radiation comes from radon in the air and uranium and thorium in the soil. You even have some radioactive carbon-14 and potassium-40 inside your body, like all living things on Earth. Plus, you're still exposed to cosmic rays right here on the ground. When you fly, you're just exposed to more since there's less atmosphere above you. Around the world, all this background radiation gives people an average annual dose of 2.5 millisieverts. That's one of the units used to describe radiation. In the US, it's more like 3 millisieverts per year. The International National Commission on Radiological Protection recommends that you keep your annual dose, beyond all that background stuff, under 1 millisievert. To put that in perspective, you'd have to fly back and forth from New York to London for around 200 hours to reach that number. But going a little over isn't necessarily dangerous. Most pilots and flight attendants have recommended dose limits of 20 millisieverts per year, or 6 millisieverts per year if you work in the EU. And the risk of cancer is only thought to increase with doses of around 50 to 100 millisieverts per year, which is way above any exposure from flying home a couple times. Some studies suggest that flight crews have an increased risk for some cancers and reproductive disorders. Like one 2009 study from the National Institute for Occupational Safety and Health showed that pilots with more flight experience had more chromosomal translocations in their DNA. This is basically when parts of your chromosomes switch places when they shouldn't, and it's widely accepted as a sign of exposure to ionizing radiation and some risk of cancer, especially leukemia and lymphoma. But there are also studies that suggest flight crews don't face any increased health risks, and should just be aware of how much they're working if they're pregnant. So science is still working on this one, but as a passenger, you've got nothing to worry about.
Good to know. I'm glad I don't have to worry about a thing I'd never thought about until just now. Speaking of things I never thought I had to worry about, here's why an Arizona airport had to cancel dozens of flights after it got too hot to fly.
Back in June, it was almost 50 degrees Celsius in Phoenix, Arizona, 120 degrees Fahrenheit, like half of the way to boiling. Whatever way of imagining this you want to use, this is way too hot. I grew up in Florida, and I draw the line at weather that's hot enough to help you cook a gator sausage on the sidewalk. This heat wave had an unusual side effect, one that made headlines because it's so foreign to those of us who don't live in places that are basically the surface of the sun. More than 40 flights were canceled because it was too hot to fly. And it wasn't a problem with the planes themselves, like it wasn't too hot inside. The air, the atmosphere, just wasn't dense enough for planes to fly safely. The strength of the lift, the force pushing a plane off the ground, depends on how many air molecules are flowing past the wings. The more molecules there are, the more of a push the plane gets. So planes have big, tilted wings to hit lots of molecules, and they speed down the runway to ram through as many as possible. If all goes well, enough molecules are pushing past the wings at the end of the runway to get the plane up in the air, which almost always happens. But if there aren't enough molecules flowing past the wings, the plane just won't lift off, and that's no good. Besides the fact that you're not gonna get anywhere, you do not want planes, like, still on the ground when the runway ends. Airports at higher altitudes where the air is thinner have longer runways so that planes can speed up more and catch enough molecules to get themselves in the air, which is why mile-high Denver, Colorado has some of the longest runways in the world. But temperature also matters. Air molecules move faster at higher temperatures and slower at lower temperatures, which kind of makes it seem like higher temperatures should help planes. You would think that faster molecules would get you more lift. But the molecules in a gas are also constantly bouncing off of each other. The faster they move, the further away they bounce after each collision, and the more spread out they are. So warmer air in the atmosphere is less dense than cooler air. And the number of molecules moving past the wings matters more than the speed of those molecules. Wings speeding down a runway through nice, cool, dense air move through lots and lots of molecules, so they get plenty of lift. But when air is too hot, the molecules are too spread out to lift the plane up by the time it's at the end of the runway. Higher temperatures also make planes' engines less efficient, which makes it even harder to catch enough molecules in time. Airlines can lighten planes by removing passengers or baggage, but that only works up to a point. For safety, some commercial airplanes aren't supposed to be flown at temperatures above about 50 degrees Celsius. So that's one more reason that I'm glad that I do not live in a place like Phoenix. If it gets too hot, you cannot escape by flying somewhere else. Thanks for watching this episode of SciShow. If you are in Phoenix, I'm sorry about the fact that you live in Phoenix and also about insulting your town.
All I know is that I'm glad somebody thought of that, because even though flying metal tubes seem to defy all sorts of rules, they are still beholden to the laws of physics, like everything else, and that means they have limits. In 1947, scientists figured out how to get around one major limit, the speed of sound, and create planes that could break the sound barrier. And there's a trick to it, but it's not as complicated as you might think. Here's Michael with the surprisingly simple secret to supersonic flight.
When the Wright brothers made their first flight in 1903, people had been trying to fly for centuries. So even though their plane didn't go much faster than 10 kilometers per hour, basically running speed, It was a major achievement. What's maybe equally amazing, though, is that it didn't take another few centuries for us to achieve supersonic flight. Chuck Yeager became the first person to fly faster than the speed of sound, more than 1,200 kilometers per hour, in 1947, not even 50 years after the Wright brothers. But making that flight wasn't just a matter of building stronger engines. To do it, engineers had to solve hundreds of problems, including ditching one of the biggest assumptions in aerodynamics. They clearly did it, though, and today the innovation that helps keep supersonic planes from falling apart is also the main reason why just about all commercial airplanes look the same. At first, making a faster plane was really just about building better engines and structures. Except, as we got better at flying and started approaching the speed of sound, we noticed that our aircraft just didn't behave like they were supposed to. We first noticed this with propellers. Propellers act like sideways wings, and because they're moving with the plane and spinning, they cut through the air a lot faster than the rest of the aircraft. But once propellers got moving faster than about half the speed of sound, they suddenly stopped producing as much thrust as expected. And at high speeds, regular wings also didn't get lift like they did at low speeds. So a plane that flew perfectly at 15% the speed of sound might fall out of the sky at 60%. The problem lingered for about 15 years until an aerodynamicist named John Stack found a fundamental flaw in the models and equations everyone used to understand how air moved past objects. In 1933, after looking at experiments in wind tunnels, he realized that air pressure around quickly moving objects drops, because ultimately the air is getting squeezed. That might not seem like a big deal, but it actually violated one of the biggest assumptions in aerodynamics. For decades, people had assumed, in one form or another, that air is incompressible. It doesn't squeeze or stretch as it runs into things, but instead just glides by or bounces off. In other words, air pressure might change from place to place, but its density doesn't. This assumption means that you don't need to worry about air interacting with itself, or how that interaction affects the rest of the world. That makes calculations way easier, and at slow speeds at least, it's mostly true, which is why people hadn't had to worry about it. But John Stack and other researchers showed that as you approach the speed of sound, thinking that air is incompressible is just flat out wrong. And it has to do with what the speed of sound actually means. Essentially, it's just how fast information, like that a plane is coming, can get passed between groups of air molecules. When a plane is going slowly, molecules can push each other out of the way long before the aircraft gets to them. But if the plane is going close to the speed of sound, there's no time for the air to move, so it piles up. That forms a shock wave that acts almost like a shield. It blocks other air from smoothly moving past the plane, decreases lift, and increases drag forces that slow the aircraft down, which explained why wings and propellers become less effective at those high speeds. After this realization, engineers developed all sorts of clever ways to mitigate this problem, from stabilizers that stopped shock waves from tearing planes apart to giving planes rocket engines that fought the extra drag. These innovations all culminated in Chuck Yeager's famous flight in 1947. But supersonic or not, shock waves still threatened to tear planes to pieces. So before high-speed flight became a regular thing, engineers had to make a change to the wings that you can still see on just about any fast plane today. Originally, most planes had wings that went straight out sideways, perpendicular to their bodies. That let air move over as much surface as possible, generating as much lift as possible. The problem was, if a shock wave formed, air didn't have anywhere to go. It just kind of piled up in front of the wing, which led to all those lift and drag issues. So engineers came up with an alternative. Swept wings. They're wings that come out of the plane's body at an angle, usually with the wings pointed back towards the tail. The angle meant that the air could get pushed along the wings instead of piling up around them, sort of like sliding down a ramp instead of running into a wall. The fact that swept wings kept air moving more than made up for having slightly less air going across the wings, creating lift. And you see this design everywhere today, from military planes to commercial jets, which fly about 70% the speed of sound. These designs all fundamentally take advantage of the same clever piece of engineering, which is why they all look pretty similar, and why the basic airplane design hasn't changed much in the last 50 years. Because once you've found a solution, you don't always need to keep switching things up.
These days, most planes fly well under 1,000 kilometers per hour, which is much slower than the speed of sound. But even though supersonic jets aren't in use anymore for commercial travel, future planes might break that barrier again. Here is what the future of air travel might look like.
Why can't I just get on a plane and go from, like, Montana to London in a couple hours? I just want to experience the thrill of zooming through the sky faster than the speed of sound. Well, if you flew on a Concorde jet back before they were grounded, or you happen to be a fighter pilot, then you've probably experienced faster than sound travel. And some companies are looking to make supersonic flight a reality again, with new commercial planes that travel faster than the speed of sound. And someday, you might be able to fly over the Atlantic Ocean in an hour or even less. Problem is, most people don't want to fly on a plane that feels like an out-of-control rocket. And there is also the problem of faster-than-sound planes becoming ridiculously hot and unbearably loud, so engineers have some developing to do. On the morning of December 17, 1903, Orville Wright became the first human to successfully pilot an airplane, a heavier-than-air vehicle that was controlled, powered, and sustained. His flight lasted 12 seconds and crossed 120 feet of North Carolinian beach with an average speed of almost 11 kilometers an hour. By the end of the day, his brother Wilbur flew the same airplane for almost a whole minute with an average speed of almost 16 kilometers an hour. Less than a century later, in the 1970s, commercial planes went supersonic, faster than the speed of sound. A few dozen supersonic planes were in regular service, available in two models, the Concorde and the Soviet Tupolev, but the Tupolev only made 55 passenger flights from 1977 to 1978. And after a Concorde crashed in 2000, people started to fly on them less. Eventually, they just weren't financially worth it anymore, and the planes were retired in 2003. 13 years later, there still aren't any new commercial faster-than-sound planes. But soon, there might be. There are just a couple of improvements companies are trying to make first. The main challenge comes from getting past what's known as Mach 1. See, sound usually travels around 1,230 kilometers per hour, but that's not a constant number. It depends on things like temperature and humidity of the air. So when it comes to planes, it's easier to talk about speed in Mach numbers, which take into account the speed of sound in the particular place where the plane is flying. Mach 1 is just the speed of sound. Anything slower than that is called subsonic, anything faster is called supersonic. But switching from subsonic to supersonic isn't easy because the plane has to overcome the infamous sound barrier. And that could be a problem because the sound barrier is sometimes strong enough to tear away at planes and even send them crashing to the ground. The sound barrier exists because of the way sound waves travel, by compressing and stretching the air they travel through. The compressed air ends up at a higher pressure and the stretched air has a lower pressure. As the plane moves, it produces sound waves that shift the air back and forth, creating areas of lower and higher pressure. But as the plane gets faster, it starts to catch up with those waves. New sound waves start to form on top of those old sound waves, causing huge swings between higher and lower pressure air. Those differences in pressure can rattle and shake planes like toys, and there's a real danger of them tearing to pieces. Low pressure areas can also lead to drops in temperature, condensing any moisture in the air, forming a visible cloud, sometimes known as a vapor cone. The first plane that could get past the sound barrier was the Bell X-1, built in 1947. It was designed to absorb 18 times the force of gravity and modeled after a machine gun bullet. It didn't actually lift off from the ground on its own, though. It was dropped from a larger mothership plane known as the B-29, so it got a bit of a head start. By the mid-1970s, supersonic planes were ready for commercial use, with the UK and France designing the Concorde and the Soviet Union designing the Tupolev. The Concorde flew passengers from London to New York in about 3.5 hours, about half the time it would take in a subsonic commercial plane. But they only took that one route, and there's a reason they spend as much time over the water as possible: the painfully disruptive sonic boom. Like the sound barrier, sonic booms come from the buildup of compressed sound waves known as a shock wave. The shock wave heads away from the plane, which you hear as a very loud boom, so powerful that they're sometimes mistaken for earthquakes. And those sonic booms don't just happen once, like right when a plane breaks the sound barrier, they continue throughout the entire supersonic flight. That's because the sound waves keep bunching up behind the plane, then expanding outwards, creating a cone shape known as the Mach cone. So whenever the plane flies over land, people hear that incredibly loud boom. So that's why the Concorde supersonic commercial flights only really happened between Western Europe and Eastern North America. If they flew over land, odds are the people would not have appreciated the booms. But even though you can't fly on a Concorde anymore, you might still be able to fly on a supersonic plane someday. NASA, for example, is looking into how to dampen the effects of the sonic boom. One way to do that might be moving one or even two engines above the wings, where it could direct shockwaves upwards, so the sonic booms would happen in the sky rather than on the ground. Then there's the Concorde 2, which Airbus is working on. The Concorde 2 would first fly directly upward to an altitude of about 30 kilometers. Then the plane would rotate its tail fin in a way that would redirect the shockwaves to be horizontal, so you wouldn't feel them as much on the ground. The Concorde 2 would be able to accelerate up to Mach 4.5, and at those speeds, it would take passengers from London to New York in an hour. But maybe that's not enough. What if you want to go faster? The Concorde 2 would be very close to going beyond supersonic and into an even faster category known as hypersonic. When people talk about hypersonic speeds, they're generally talking about Mach 5 or higher, more than 5 times the speed of sound. Those speeds get their own category because that's when the temperature of the plane becomes a bigger issue. The plane is flying through the air so quickly that friction with particles in the air is a real problem because it makes a lot of heat. At hypersonic speeds, planes need to be able to withstand temperatures over 1,000 degrees Celsius, but almost all of the more typical metals would melt or at least become very weak at temperatures below that. The other challenge is the engine, because a regular jet engine wouldn't work. Standard subsonic planes use large rotating blades to compress incoming air, inject fuel, and then let it burn, propelling them forward. At supersonic speeds, it becomes even easier because high speeds already compress the air. In that case, the engine doesn't even need the blades. That's what's known as a ramjet engine. Ram, because the air is just rammed into the engine. At hypersonic speeds, though, this plan doesn't work as well. Sure, the air is compressed, but it's moving so fast that there's not enough time for it to combust and actually help move the plane. So hypersonic planes need their own fuel and their own oxygen, which is what NASA used in the X-15, the first plane to reach hypersonic speeds. It used a titanium skin to protect itself from the extreme temperatures and was able to fly at Mach 6.72. It also flew high enough that some of the X-15 test flights are considered space flights. But the X-15 is not the kind of plane that could be used commercially. For one thing, it burned through fuel so fast that it would run out in less than 2 minutes. Also, pilots sometimes experienced 8 times the force of Earth's gravity, and most people wouldn't consider that a comfortable business trip. So, until engines become more efficient and practical, commercial hypersonic planes are a long way from reality, and the scramjet might be the answer. Scramjet engines work kinda like ramjets do, but they're designed to handle the faster moving air. In testing, NASA found that they could work at speeds of up to Mach 15, at least in theory. There's one big drawback though: scramjet engines only work at hypersonic speeds. The X-43A, for example, an unmanned test plane that uses a scramjet, has to be accelerated above Mach 5 before it can fly on its own. It's strapped to a booster rocket, which is then loaded onto a subsonic plane. Alright, stay with me. The plane flies to about 6 kilometers above the ground, then releases the X-43A along with the rocket, which gets it to about 30 kilometers up and speeds of Mach 5. Then, the X-43A can start its flight. So it might be a while before hypersonic planes are a practical way to get across the Atlantic. But a future where a trip to the other side of the world involves flying faster than the speed of sound without painful sonic booms for the people on the ground, that might not be so far off.
Speaking of futuristic airplanes, where are all the electric planes? Even though other types of electric vehicles are taking off, it'll be a long time before planes are ready to give up their petroleum-based jet fuel. Here's Stefan with more.
Using clean, renewable sources of energy is really important for keeping our planet safe and healthy. That's not that surprising. It's why so many buildings are switching to solar or wind power, and why electric cars are becoming more mainstream. But then there are airplanes. Every day, tens of thousands of commercial flights take off around the world, and just about all of them are loaded up with thousands of liters of petroleum-based kerosene. So where are all the electric planes? Well, aircraft designers, including Airbus and NASA, are working on it. But don't get your hopes up that you'll be flying to your next vacation on a zero-emission electric airliner. For now, jet fuel is just too good an energy source to get rid of. The challenge with designing any airliner, electric or otherwise, is figuring out how to store enough energy to power a flight. Since weight and space are kind of at a premium, your plane will ideally have some kind of power source that's super effective, but also pretty light. This is something designers think about a lot, specifically in terms of something called fuel energy density. Also called specific energy, this is the amount of energy per unit volume or unit mass of fuel. Jet A and Jet A1, the most common commercial jet fuels, are about as energy dense as fuels get. They have about 43 million joules of energy in every kilogram of fuel, or about 1 liter of the stuff. For comparison, that's about the same amount of energy as if you crammed 43 sticks of dynamite into a soda bottle. Meanwhile, even the best commercially available batteries only have around 900,000 joules of energy per kilogram, more than 48 times less than Jet A and A1. The difference comes from how jet fuel and batteries store their energy. Jet fuel stores energy directly within the structure of its chemical bonds, so all you have to do is burn it. Batteries, on the other hand, store energy in charged molecules, or ions. They release their energy by transferring electrons between a negative ion, called an anode, to a positive ion, called a cathode. But to do that, batteries need a bunch of parts: an anode, a cathode, an electrolyte for charged ions to transfer through, and a container to hold it all together. And all that just takes up a lot of space. If you tried to power a Boeing 737, your classic passenger jet, with electricity, you would need a pile pile of batteries that weighed about 1 million kilograms, which is about 13 times the max takeoff weight of the aircraft. So yeah, batteries are about as good for air travel as a pile of bricks. Today, some companies are working on developing all-electric aircraft, but don't expect them to be popular anytime soon. For now, the next major steps involve building hybrid electric systems, which will be kind of like training wheels while we figure out the electric part, and maybe more importantly, making lighter and smaller batteries. Researchers are working on it though, and scientists at Cambridge have already developed special lithium-air batteries with about 10 times the energy density of current technology. But there's still a long way to go. So for now, just sit back with your seat back and tray table in their upright and locked position and enjoy your kerosene-powered flight.
And don't hold your breath, but while you wait for a futuristic airplane, there will be plenty of other developments keeping air travel exciting in the meantime. Thank you for watching this compilation, and thanks to all of our supporters on Patreon who helped us make all of these episodes. Everything you contribute helps us make science free on the internet. If you want to learn more about how you can support us, head over to patreon.com/scishow to learn more.